So constant pressure calorimetry. This is a way we can measure the heat of reaction. This works really well for aqueous reactions, and we can do this in something as simple as styrofoam coffee cups. And that's what we're going to use. So here, this is our setup, and the setup we're going to use in lab today will be very similar. We're going to use 2 styrofoam cups, nested one inside the other, and the reason we do that, this is an answer to a pre-lab question, the reason we do that is for better insulation, to minimize the amount of heat that is lost to the surroundings. And then we're going to put a lid on this. We don't have fancy cork lids. We have some ancient pieces of cardboard. Many of them are older than you are. They still work just fine. A piece of cardboard up here, it needs to be loose fitting because this is constant pressure calorimetry and we don't want to have any pressure changes. So that's loose. We're going to have a thermometer in here. Ideally, we would have a glass stirrer, but we're going to live dangerously, and we're going to use our glass thermometers to stir the solution.
You said better insulation?
Pardon me?
You said better insulation?
Yes, better insulation. We can use this as a stirring rod here because it is hard to break a thermometer on a foam cup, right? What more often happens is you accidentally poke a hole in the cup with the thermometer. We would not use a glass thermometer to stir things in a glass beaker because something's going to break there. So 2 nested foam cups open to the atmosphere, that means constant pressure. So Q for the solution is going to be MC delta T, the mass of the solution, the specific heat capacity of the solution, and the change in temperature of the solution. That's what we can measure because we've got an aqueous solution in here with a thermometer in it. We can measure the change in temperature. Why is the temperature changing? Because a chemical reaction is occurring. So Q for the reaction, all of the energy lost by the reaction goes into the solution. Or if this is heat being transferred the other way, all the heat absorbed by the reaction comes from the solution. So Q reaction equals negative Q solution. At constant pressure, the heat of reaction is equal to Q for the reaction. So we can calculate the heat of reaction. That's going to be for the specific amount of stuff that we put in there. Heat of reaction is typically expressed per mole of substance. And so to get that in terms of joules or kilojoules per mole, we just divide by the number of moles of reactant that we used. So we're going to weigh out our reactant. We're going to know what it is so we can calculate how many moles. Any questions? Let's do an example here. Addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.4 degrees Celsius to 24.21 degrees Celsius. Calculate delta H for the reaction as written. Use 1 gram per milliliter as the density of the solution, and the specific heat capacity equals 4.18 joules per gram degree Celsius as the specific heat capacity. Okay, so we have 2 things. We have the reaction and we have the solution. So there's a liquid, aqueous is water, and it's got these chemicals dissolved in it. When we mix them together, the reaction occurs and it either releases heat or absorbs heat, and that causes the temperature of the solution to change. Okay? So we can say Q reaction equals negative Q solution. This temperature change, is that the change of the reaction temperature or the change of the solution? How do we measure the change in temperature of silver nitrate when it's in a solution? We can't. We can't measure the change in temperature for the reaction. We put it in the solution, and then we can measure the stuff relating to the solution. Q solution equals the mass of the solution times the specific heat capacity of the solution times the change in temperature of the solution. Q equals MC delta T. We were told to use this for the specific heat capacity. We've got some temperatures here. We can calculate the change in temperature. And so that's C and that's delta T. What else do we need? We need the mass. Now in lab today, what we're going to do is we're actually just going to stick the coffee cups with the solution on the balance and weigh them. We know what the empty coffee cups weigh, and so you just subtract and we'll get the mass directly. They didn't give us that information here, but they gave us the volume. We got 50 milliliters of this thing and 50 milliliters of that thing, so the total volume is 100 milliliters, right? We have 100 milliliters of solution. They told us to use 1 gram per milliliter as the density. So my mass then is 100 grams. My change in temperature, final minus initial. Final temperature was 24.21. Initial is 23.40. 24.21 minus 23.4, 0.81. So Q for the solution is equal to the mass, 100 grams, times the specific heat capacity, 4.18 joules per gram degrees Celsius, times the change in temperature, times 4.18 times 0.81 equals. Based on my temperature change, I should have 2 significant figures. And then let's check out the units here. The grams cancel and the degrees Celsius cancel, and I'm left with joules. This is telling me that the solution in my calorimeter absorbed 338.58 joules of energy. That came from the reaction, right? This is equal to negative Q for the reaction. So that means that Q reaction is what? If negative Q reaction is this number, then positive Q reaction is the opposite, the negative. Negative 338.58 joules. They want me to calculate the heat of reaction for the reaction as written. So delta H reaction is going to be some number of joules per mole amount of these guys. It could be 1 mole of this, it could be 1 mole of that, right? do the HCl. So how many moles of HCl is this Q for? Well, we used 50 milliliters of 0.1 molar. Like completely run out of room here. 50 milliliters times 0.100 moles per liter. Gotta change those milliliters. At 0.005 moles. Let me check my math. 50 times 0.1 times 1 EE minus 3. 0.005 moles. 0.005 moles of HCl gave off this amount of energy. So I can take minus 338.58 joules, and that was for 0.00500 moles. So for 1 mole is going to be more energy, right? So take my 338.5 and divide by my number of moles. And I get a really big number. 67716. It's negative. Yeah.
Conversion of the AgNO3 milliliters. I'm just getting lost with the
Okay, so we're calculating the amount of energy released for 1 mole of HCl or for 1 mole of silver nitrate. Now we do have 2 reactants, and so we could have a limiting reactant problem here, but we don't, because we have the same number of moles of each reactant. So we could choose to look at either one. So this is the amount of energy that was released per 0.005 moles of HCl or 0.005 moles of silver nitrate. So we divide by that, and that'll give us the amount that would be released if we had 1 mole of that.
Just in terms of the 50 milliliters, trying to cancel out with the 1 liter of 0.100 moles.
So in here, I took the volume times the molarity, and then the units weren't working out, and so I put a conversion here. So this milliliters cancels here, and this liter cancels there. That's only supposed to have 2 significant figures. We could write that in kilojoules, but we're going to say minus 6.8 times 10 to the 4th joules. Any questions?